pleasure to introduce Dr. Silke Weinfurtner, with whom we are today continuing the celebrations of 100 years of Einstein's theory of general relativity. I'm sure many of you were here 2 days ago when we had a talk by a guest speaker from Oxford, Professor Pedro Ferreira. So today, next week this time, and the week after this time, we are having talks by local experts in Nottingham who are working on aspects of Einstein's theory and are here to tell us about those aspects of Einstein's theory. So the plan is today we'll have a talk of approximately 40 minutes, and then there will be a question and answer period. The speakers have taken great pains to make the topic understandable without extensive advanced study at the technical level in the topic. This is a talk for a general audience. So when the question period comes, please do not hesitate to ask questions. Okay? Now, I do see that there is significant expertise in the room as well. So if there come questions on which the speaker may wish to direct the question to an expert in the audience, experts be warned, this can happen. On a converse note, experts, please be warned, if you spot an equation where you start wondering, is the sign in the second derivative term really the correct one? If that's your question, maybe you could sit on that question for a little bit and start with more general questions when the question period starts. So I believe we are ready to start. Let me just tell a few things about Silke. So Silke started her studies in Germany, in Munich, then went to do a PhD at Victoria University in Wellington, in New Zealand. She had postdoctoral research positions at the University of British Columbia in Canada and at the International Center for Theoretical Physics in Trieste, in Italy. And starting last year, Silke is now here in Nottingham as a Royal Society Research Fellow, as well as a permanent academic staff member here in the School of Mathematical Sciences. She also holds a visiting research fellowship at the Perimeter Institute for Theoretical Physics in Waterloo in Canada. Silke is one of those rare persons whose expertise bridges theory and experiment. On the theory side, Silke is interested in quantum phenomena in curved spacetime, particularly spacetime of a black hole. On the experimental side, she is interested in modeling these curved spacetime phenomena in a laboratory system, doing concrete experiments. Silke's research has received significant recognition. For the purposes of tonight, let me just mention one. Silke's water tank experiments were mentioned and indeed used as a plot device in the television comedy show The Big Bang Theory. And there are few living scientists who can boast that sort of recognition. So without further ado, would you please join me in welcoming Silke Weinfurtner.
So thank you, Yama, for this very nice introduction. So today it's about general relativity's legacy, and this is a truly remarkable, beautiful, and to some extent a bizarre theory. And in particular, all of the talks are about how general relativity has changed the way we look at the world, has changed the way we do physics. And today's talk is about how it changed the way we look at our universe. And what we're talking about is about black holes, strange stars, and ripples in space-time fabric. And when I was looking for suitable pictures for the first slide, I was very happy to find this because it contains all of today's subjects in one picture, and we will come back to it at the end to identify the various objects. So the first thing when you look at this picture is what really is the most dominant theme here is this white mesh. So this white mesh is the artist's representation of what we refer to as a space-time fabric. So, and because of that, I have to first say the space-time fabric or space-time geometry plays an important role in Einstein's theory of gravity. So let me go back and just briefly summarize what this beautiful theory is about and what the key features are. So before Einstein, when we thought about gravity, actually not me, I was not alive, but when people thought about gravity, it is Newtonian gravity discovered by Sir Isaac Newton in 1665. And he postulated his theory of gravity where he said that any two massive objects, bodies, experience a gravitational force, a force that will be accelerated towards each other. And this force is directly proportional to the masses of the objects and inverse proportional to the distance of these objects. Now, if I look at two pens, for example, so why don't I see that they're being accelerated towards each other? It's simply because their masses are very small, but also that this capital G here is a constant which is extremely small. It's this Newton constant. And what it means, in order to really experience a gravitational force, you have to compensate this very small number here with a very large number in terms of that at least one of these objects is very massive. So for example, our Earth. So but the important feature here is that gravity is a force. So that was before Einstein. And then when Albert Einstein in 1916 and 1915 postulated his theory of gravity, his theory of general relativity, he changed all that. And what he said actually, it's not that it's these strange forces acting on each other, but if I have any massive object, or very massive, let's assume a very massive object like our Earth, it wraps space and time around it. And he said space and time first has to be unified as one object called space-time, and massive objects wrap this space-time. And if I then, for example, take a small object like a soccer ball or so, it would simply following the world lines in this space-time geometry, this space-time fabric, and would be freely falling, free from any external forces. So this is Einstein's view of the gravitational field. So this wrapped space-time directly presents a gravitational field. And then he also gave us something else. He said, okay, so this is the gravitational field, but he also gave us a dynamical solution. He said, if I have some object, some massive object, I can calculate how it will wrap the space-time around it. And this is referred to as the Einstein equations. So by looking at the Einstein equations, you can see what kind you can solve for various space-time wrapping. And so this is what we're going to do. We look at the various wrappings of space-times that there are in our universe and how they affect the way we look at the universe today. So, but before we start this, I have been told that it's very important in a public talk to give a practical example. So before we really address the very fundamental questions in our universe, let's do something very practical. So I'm very terrible in orientation, and I heavily depend on the GPS. So GPS, all of you know, that's a global positioning system, and it's a space-based navigation system with various satellites orbiting our Earth, and it provides us with a location, exact location in location and time anywhere on the Earth. So however, general relativity predicts that clocks, when they are closer to massive objects, they tick slower. So when you look at the GPS system, you have clocks based on Earth, and you have clocks in your satellites. So and there's a mismatch on how time passes in these two clocks. And this gives a time, this time difference has to be accounted for in order for this GPS to work accurately. So this is a very practical solution, so which helps me tremendously to find my way through new cities. And now let's move on to the more fundamental questions. So the first thing we're doing is we start the most basic question: what is a star? So we're looking at this object here in these pictures. What is a star? But what we want to ask is a bit more deeper. So this question, what is a star, is perhaps one of the most fundamental questions in the universe. It starts with lullabies for babies. The question, little star, how I wonder what you are. Let's go beyond that question and say, I wonder how you came about, and I wonder what will become of you. So a less romantic way, if you look at what a star is, and you go on Wikipedia and you Google, you find, well, a star is a luminous sphere of plasma held together by its own gravity. So it is really gravity plays an important role. So, and in fact, gravity determines the whole life cycle of a star. And one thing is very important is the most famous example for a star is the sun. It's the nearest star to our Earth. And it is important throughout this talk because the sun is 1 solar mass. So everything we talk about, so the sun has 10 to the 30 kilogram. It's very hard to work with this number, but when I talk about it, I talk relative masses. Everything is compared to the sun. It's 1 solar mass. So let's move on. So there is, of course, there are a few more details, but you can simplify all of this difficult life cycle of a star and collapsing it into this simple slide. So what you can start first in our universe, we have molecular clouds, interstellar matter, and then there can be pockets where the gravitational force is dominating over pressure, pushing the clouds, the molecular cloud outwards, where gravity wins, and you can form a star. So it's called gravitational collapse. So in these dense pockets in our universe, stars are being born, and then you can ask yourself then, so if gravity is so strong, why does it stop there? So when you compactify, or you have this extreme dense matter, you start in the core of the star nuclear fusion, nuclear physics, nuclear processes that prevent the star from collapsing further. So in fact, our sun and every star is just sort of a quasi-equilibrium state where the gravity it's the nuclear fusion of the star is fighting against the gravitational collapse. So the very thing that created a star is now about to destroy it. And then when you, depending on how massive this star is, and the mass is the main indicator here, that determines the fate of the star. This gravitational collapse continues, and there are now 3 choices. You can end up as a white dwarf, a neutron star, or a black hole. And I would like to discuss case by case what the differences are and how they came about. So what is a white dwarf? So a white dwarf, that's the future of our sun. In 6 billion years from now, the sun will be collapsed to what's referred to as a white dwarf. So this is a picture of our sun. Let's look inside. So as I mentioned before, you have this nuclear fusion which prevents the sun to collapse, which prevents the gravitational collapse. So at some point, the nuclear fusion comes to a halt. They run out of nuclear fuel. And what's happening is gravity then wins and compactifies the star further. So the question is, why does it not completely collapse? Why is it stopping at the white dwarf state? So the reason for that is, it's quite spectacular, and it's a beautiful part of physics, which also involved a Nobel Prize for Chandrasekhar, which is beautiful physics, really, if you think about. So you have this massive classical object, and it collapses, and suddenly what happens, quantum physics matters. So what you're mainly left with after this nuclear fusion is a lot of electron gas. So if you want to compactify these electrons further, what's happening is these electrons are fermions, and they're weird particles. They don't like each other so much. So when you wanna stack them together, then you have to sort of like, you have an availability of energy levels. They have to have certain energies, but they don't like each other so much. So you can only have 2 of them at one energy. So a simple example to understand that would be, let's look at the parking space. So for example, if you come to university before around 8 o'clock, this is a situation you find. You find plenty of nice parking spaces. And cars going into the parking can quickly move in and park. Once the parking lot is filling up, it's harder and harder for the cars to get in to find these single spots. So the rate in which it can go in is slowing down. And this is somehow, with these electrons, it works in the same way. It's called electron gas degeneracy, and that prevents the star from complete collapse. So this is an artist's depiction of our sun as it collapses. So here we're on 6 billion years from that now. The star is collapsing, it goes through what's called a red giant, and it ends up as this very compact object which has some remnant temperature, but nuclear fusion has stopped. And it's just held apart, it's just prevented from collapse due to this electron degeneracy. Now this is an artist's depiction, but clearly it's not quite, the scales are not quite right. So if this is the sun, it will shrink down. The white dwarf will have the size of the Earth. So it will have collapsed about 109 times of its original diameter. So, however, if the mass of the star is even bigger, it can overcome this electron degeneracy and it can collapse further. And what forms are these extremely compact objects which we are referred to as neutron stars. And they have a radius of about 11 kilometers with the mass of about twice the sun. So these are really heavy objects, very compact heavy objects. Now, what is happening here is, before we said, if you have a star which a mass less than 1.5 times than the mass of our sun, so solar mass, it will collapse into a white dwarf. If you have an object, a star, which is heavier than that, which has more mass, more massive, it can actually, gravity is stronger. And when it comes to this process, there will be, at that stage when it compactifies, there's enough gravitational force to combine the electrons left over from the nuclear fusion with protons and form neutrons. And then the same game happens again. There's your neutron degeneracy, gas degeneracy, which then determines the final size of this object. So these neutron stars have a very particular feature. They are heavily rotating, and that is, of course, that there's an easy way of understanding that. So if a star is collapsing and it had already a little bit of angular momentum, or the collapse is not completely spherical, it will accumulate angular momentum during this collapse. Now, what happens actually is, it's the same effect if you look at an ice skater. When spinning, there's very little friction with the bottom, with the skaters. And then what's happening is, when the angular momentum is conserved, and when you pull in the arms and the legs, you have a decrease in the moment of inertia, and as a consequence, because angular momentum has to be conserved, the rotational speed has to increase. And this is what happens to these neutron stars. They, because of their extreme compactification, they acquire extreme rotational speeds. And then one of the objects which is very important, and we will talk about a lot in the next few slides, is a pulsar. So a pulsar is a highly magnetized rotating neutron star that emits a beam of electromagnetic radiation, which actually helps us to observe these objects. And these spirals here are the magnetic field lines. So, but why I'm talking about these pulsars, one of the really exciting discoveries was a binary pulsar system consistent of 2 neutron stars. And that was a very special system, because here's this schematic picture of this binary pulsar called PSR 1913 plus 16. 2 neutron stars cycle each other closely in elliptical orbits. The mean separation is only a few times greater than that of the Earth and the Moon. One orbit takes only about 8 hours. And what was so fantastic about this discovery is, they looked at the orbits of this binary pulsar system over a long time period, and what they saw is that these orbits were shrinking. What that meant is that energy was being given away from this system, so something was missing. So, and what was missing, there was a prediction from general relativity that says what's actually how the energy can be radiated away from this system, and that's called gravitational waves. And now we are at the ripples in the space-time geometry. So when you have a binary pulsar system and they orbit around each other all the time, they emit these gravitational waves. And gravitational waves are the ripples in space-time fabric that propagate like waves with the speed of light. And this is how you could think of that. And then let me talk about some very peculiar features of gravitational waves, which are also very essential actually for their detection. So if a gravitational wave passes a distant observer, that observer will find space-time distorted by strain. So if I take a gravitational, so I have a ring of particles here, and let's assume a gravitational wave would travel into the screen, perpendicular, on an axis perpendicular to the screen, through this circle here, then the gravitational field would distort this circle. And there are two ways of doing this. There are two kinds of gravitational waves. And the one is called the plus polarization, and the other one is the cross polarization. And when you look at this simulation, that is a plus polarization, where you have a distortion of this kind with 90 degrees in between, and then you have the cross one with 45 degrees in them. So this is how these circles will be affected by gravitational waves. So now let's go back to this extreme, amazing observation. So what they have seen is an indirect proof of gravitational waves. So, and that was such a big discovery that gave Joseph Taylor and Russell Hulse the Nobel Prize in physics for the indirect detection of gravitational waves. So, but now, of course, indirect is nice, but it's nicer to do it directly. So, in order to do it directly, we have to look at how big is that actually distortion of space-time, of the space-time fabric from these gravitational waves. So when I had this picture here, what I had like this ring, this deformation, it was about 50% in amplitude. That is very extreme. So, but how big was these waves? How much were the waves when I observed them here? How big a distortion of space-time would I get from this binary pulsar system? And the answer is, it's if I have a length, if I look at the length of a meter or any length of 1, the distortion, the change in the length is 10 to the minus 22. So that's a lot of zeros. Another way to look at that, I could look at it, how many zeros in terms of the size of an atom. And it's a billionth of the size of an atom. So this, it's very hard, I mean, it's impossible to see this particular event, but there are certain ways of enhancing this detection and also bigger events, so that in fact there have been big missions going on to hunt the small, and we will discuss them, but obviously one of them is to increase the length scales over which I look at the deflections, and the other one is I use this particular way the gravitational field travels, the polarizations. So what one uses here are this, in these big missions, is this interferometers, Michelson-Morley interferometers. So let's look at this thing here. You have a laser light with a fixed wavelength, and you send this wave in here. There's a beam splitter which simply divides this laser beam into two. One is going up here and the other one is going through, and both ends, they are mirrors that just reflect these beams back. They come down here and they're being detected. Now, depending on the distances the light is traveled, you can have, maximally, you can have this destructive interference or constructive interference. So destructive interference is if you match the wave in the way that if there is a minimum, here is a maximum, then what you see is nothing. But if you constructively interfere them, two maximum enhance each other, and you have a bigger signal. So what it means is if I have these detectors here, and they change the length, as for example a distortion in space-time would do, you can actually see these tiny interferences in your detector here. So this is what you do. So this was the trick of using this polarization, because again there is a relation of how these detectors have to be moved. And then you can look at what are the big missions. Big missions in all means really, is big scientific goals, big money, and also just really large scales. So these are these Earth-based missions here, LIGO and Virgo. And what you have here, you see these interferometric arms, and the arms are 4 kilometers, but then you use a trick, you bounce back and forth a few times, so the distance traveled by this laser here sums up to about 100 kilometers. Now, of course, there is a lot of noise in here, but one thing you can do to make these arms even further, even longer, and to reduce the noise is to send the whole thing up in space. And that's what's called LISA, or now iLISA, evolved LISA. And this is this planned space-time mission where the arms are separated by 5 million kilometers, if I remember that right. Sorry. So that's how you can enhance this effect. But let's now, let's now listen to one of these gravitational wave detectors. How would it look like? I can take what I see in these detectors here, and I can take this, and because, for example, the frequency band LIGO gets is in the acoustic regime, so I can convert that to acoustical wave and I can listen to it. So this is how it sounds like. I think, that's a pity, I cannot hear the sound. So basically what you should hear is just a bunch of noise. So the thing is, because there's so much noise, you need to know what you're looking for. All this signal is completely buried in the noise. So how can we know what we're looking for? So this is an amazing part, which I really love about gravitational waves. So what people have started, they have started to run numerical simulations of all these possible events where we expect gravitational waves to be emitted. Binary pulsars, supernova explosions, and so on. And what they do, they run these simulations to predict what kind of gravitational waves, what we would see at our detectors. So, for example, you have this binary pulsar system here emitting, and then what happening, you see the gravitational waves being emitted here, and then here below you would see what you see at the detectors. And so unfortunately I also had this sound which is like a chirp at the end when the two things finally merge. But so we need to know what we're looking for. But then obviously there are so many events. So what people have started to do, they have started to create a catalog for these ancient events, for all possible events, all possible space-time wrappings, and how they would look like in our gravitational wave detectors. So this is a worldwide effort, and I think it is an amazing project, and to really hunt the small in a collaborative way. So one of the special events which was on the slides is like we haven't discussed. And I would say these are we're now coming to the most bizarre and most fascinating objects predicted from general relativity, and which are black holes. It's also what I'm working on. And what you see here, in some sense, you see these punctures of space-time, and what you see here, this is a big black hole and a small black hole orbiting each other. And so, what is a black hole? Already in this picture again, here there's the depiction of a black hole in here. So black holes form when the masses of the star exceed about 3 solar masses. So then nothing can prevent gravity, nothing can prevent the gravitational collapse, and gravity finally won. So this is what you get a black hole, all of the quantum physics, everything can be overcome, and you have this extreme, you compactify the star further and further and further. So 1 year after the discovery of general relativity, 1916, Carl Schwarzschild tried to solve the Einstein equations, and he looked for spherically non-rotating solutions. So solutions where it doesn't matter if you have the origin somewhere, origin of a star, for example, doesn't matter in which direction you're looking, it's non-rotating, it only depends on the distance from the origin. And he solved that, making this assumption, and he found these Schwarzschild black holes. And what was so remarkable about that is that he found that if the mass of a star would collapse beyond what is called the Schwarzschild radius, you form these black holes, and they are very particular because the Schwarzschild radius, or what's called is like you can think of, you have the mass of all the mass shrinks down to a point, and around it you have this this horizon, which is also referred to as this event horizon, and the gravitational pullback in this area is so strong that nothing can escape, not even light. So you have inside these regions of space-time, things are trapped for eternity. So let's discuss, so how much would I have to collapse objects so that I can form a black hole? So if I, for example, take what is the Schwarzschild radius, let's forget for a second about electron gas degeneracy. What if I would like to collapse Schwarzschild radius of the sun? It would be 3 kilometers. For the Earth, it would be 9 millimeters. And if I would take the Mount Everest and I would like to condense it, I would collapse it to a black hole, I would have to have it below a few atoms, the size of a few atoms. So this is what is needed to create a black hole. So actually, I just noticed I forgot a slide to add, which I wanted to add, and what is a really important slide. So how do we know that these objects really exist? There has been, in the center of our galaxy, there is supposedly a massive black hole, a supermassive black hole, and you can see that because, as already pointed out many times, space-time is wrapped so strongly around it that it highly influences other objects traveling around it, planets, stars, and so forth. So there is the general consent that there is a supermassive black hole in the center of our galaxy. So, but black holes also, really strange physics is happening around black holes. So, for example, as I said before, if you're within the event horizon, light cannot even escape. But even if you're outside in the vicinity of black holes or vicinity of neutron stars, what can happen? You can have very strong light bending, which is referred to gravitational lensing. And what you can see is that light, if you look at that, you send a light here, you can see things which are actually on the other side of your star, for example, or if in certain orbits you can look actually at the head of the back of your head. So there is such a strong light bending due to the wrapping of space-time geometry. Now here I found this nice animation online where you look at the Earth going around a neutron star and how it would look like taking into account the gravitational lensing. So it looks like it will wrap around this massive object, and it's not really happening, it's just a distortion of the light being sent off from this system. So they're really like these massive objects, like super lenses. So in some sense, the life cycle of a star does not quite end here. And in particular, there is another process, another layer in the story of a star if it is heavy enough to collapse to a black hole. So the question is at the end of it, will it just be this black hole and the mass will be trapped inside the event horizon, or what's happening? And in fact, very strange things happen around these black holes. So in 1974, Stephen Hawking discovered that black holes can actually evaporate. So what he did is he said, okay, everywhere in our universe there are quantum fluctuations. So when you have in systems, you can easily imagine in water or in anything like, let's take surface of a water. And let's say when I shake, I have it in a basin, a container. When I shake it, of course, I have some vibrations on it. But then I can, of course, keep it completely still. But then I also have some thermal noise. I can still have some fluctuations. But there is one thing which I can never get rid of, even if the temperatures are going to zero, and that is the quantum noise, the quantum fluctuations. They're everywhere. And they're also around the black hole. So what a black hole does, it takes these quantum fluctuations and it splits it, it separates it. It separates it into positive and negative energy. And what it does is actually it sends away the positive energy in form of a thermal radiation, which I will come back in a bit. And at the same time, it absorbs this negative energy. And absorbing negative energy means actually energy is taken away. And the way it works, the black hole has a mass that has some energy. And so through this negative influx, it can actually consume its mass. It slowly evaporates away its mass. Now, and if you look at the outflow, so simplified, you can say I have this thermal radiation, it looks like a black body. So for example, what is thermal radiation? If I have a nail and I heat it up with some fire, it starts glowing with a certain color here. And this just means if I have like the intensity here or the wavelengths given up here, photons given off, then where the peak is, that determines the color. So thermal radiation has a peak and that determines also where this is. For example, you can see it glowing bright yellow. So, and black holes are like that. They take these vacuum fluctuations around them, and you can, through this thermal radiation, you can associate a temperature to that. And this temperature here, so this color here is linked to a particular temperature, sorry. So, and black holes also, you can associate the temperature to them. And then the way to look at that is you have the black hole. It has a certain mass, it has a certain temperature, it starts this evaporation process. During this process, the mass is getting reduced. So the temperature, however, is inverse proportional to the mass. The smaller the mass of the black hole, the higher this temperature is. The higher the temperature, the faster this radiation process becomes. More radiation will be given off. So while it goes down and reduces its mass, it changes more rapidly. The change in the mass becomes quicker, till it finally gives off all its mass, and it's a runaway process till it makes plop, and the black hole is gone. So that is Hawking radiation, and in some sense, that will be the final cycle of these supermassive black holes, which have been created in pockets, in strong, dense pockets in molecular clouds. So the question is, do we know that that really happened? And the answer is no, otherwise you would also see some sort of Nobel Prize here for Stephen Hawking. So it has not been discovered, and the reason why it has not been discovered is because these temperatures are really, really, really small, and these black holes are really, really far away. So, and they are small because you can say, well, this temperature depends highly on the mass of the black hole, and then one can look at the universe and can make estimates and say, what is the smallest black hole which I believe to be out there? And still, which are black holes which have to be formed through the Big Bang, so initial primordial black holes. And what one can see is that these temperatures are still so small, there's simply no hope of directly detecting them. So in some sense, this is an open question. I think many people believe black holes do evaporate. However, this is an ongoing line of research. And I'm almost at my last slide, and I'd like to talk about my kind of work. And that is by saying, well, this is a really difficult problem. We cannot attack that. We cannot observe this Hawking radiation. But we can do something different. Although these effects seem particularly strange and bizarre, we have discovered that this kind of physics reoccurs in other systems. And these are called analog gravity systems. And these analog gravity systems are nice because they are everyday system, or very easy or accessible. Not all of them are easy, but accessible system, which we can set up in tabletop experiments, and where we can try to mimic some of this bizarre physics that allows black holes to lose their mass or their angular momentum in an experimental setup, to testing for the universality and robustness of these effects. So, and I want to explain you just in a few words what an analog gravity system is and how you can see a black hole horizon in water. And as I said already before, this is twofold because I'm working on this, but also it provides you with a very simple example which you can tell your friends, which you can tell your children, how black holes conceptually work. So the analog black hole is a very simple system. We're looking at a river flow. And what we have here, we say that it's a one-dimensional river flow. And what we're assuming is that the velocity is increasing from the left to the right. And when I'm at this point here, we're looking at sound waves in the system, small excitations in the system. And what I'm looking at here is I say, okay, I'm exciting here sound waves, and the different colors show you how the sound waves is propagating through water at different times. So starting from the yellow to the dark blue. So if the river is almost at zero, sound waves can propagate equally fast in both directions. If you come now to the point where you have a significant background velocity here, you can see that, of course, the sound waves propagating with the flow are much faster, travel a greater distance in the same time as the ones that travel against it. So let's now hypothetically say, what if I can exceed the background velocity to the speed of sound in this system? Then you can imagine here at that very point where I have my background flow is equal to the propagation speed, all the sound waves are now getting dragged downstream. So, and this is what's called a sonic horizon. So, and if I'm beyond this point, all the sound waves and fluctuations initially they're going downstream. So I cannot communicate from being inside from this region if my means of communication is a sound wave. I cannot communicate or send signals to somebody being on this part. So what you create are these causally disconnected areas, and what you can show now in these systems is that some of the physics, this bizarre physics of how you lose angular momentum, how you lose your mass, black holes losing mass, also there's another process that allows black holes to lose the angular momentum. How you can mimic that in simple systems where you have these effective horizons appearing. And I'm finishing in time, perhaps even a bit early, that's my first. So coming back to this picture as I promised you, it's a landscape, how I look at it. It's a landscape, it's a beautiful landscape. It summarizes everything that there is in our universe, almost. It's a landscape painted by, this is a young Albert Einstein. And what you see here is a star. We have discussed how stars have been born, how they collapse, have born due to gravitational collapse, how they've been further collapsing to white dwarfs or neutron stars, or to black holes. And what you see here is also these ripples in this white mesh are the ripples, the gravitational waves in the space-time fabric. This is an ongoing line of research. By no means we know everything. It's quite the opposite. The deeper we look, the more questions appear. I think it's a really exciting line of research. Looking forward to see the first gravitational wave detection. And what I want to say, so coming back to all this, I was really walking on the shoulders of giants throughout this whole talk. Of course, Albert Einstein also received the Nobel Prize, and perhaps Pedro has talked about this, but it's really amazing that all of what I talked about, this great discovery, the Nobel Prize was given for something different. So I think it's one of the rare cases in history where there's one person that I could imagine easily has deserved 3 Nobel Prizes. Thank you very much.